My name is James Hood, and I'll tell a little more about me later. This webinar is called Nested Applications, Accelerate Serverless Development using AWS SAM and the AWS Serverless Application Repository. Again, my name is James Hood. A little bit about me. I'm a senior software development engineer with AWS. I work specifically on the AWS Serverless Application Repository and AWS SAM. I have 15 years industry experience in software, and I've spent the last 9 years of my career at Amazon. Also in that time, I've worked both in AWS and also within Amazon retail. So I have experience both inside of AWS, but also on the retail side where we're just another customer of AWS. I also have my Twitter handle on there. I'm pretty active on Twitter, and that's a good way to reach out and contact me if you need to. So what are we going to talk about today? First, we're going to start with what is a serverless application. Then we're going to talk about challenges with serverless architectures specifically compared to traditional architectures. I'm going to cover 2 challenges in particular. And then I'm going to talk about a solution to these 2 challenges, which is this feature of nested applications with the AWS Serverless Application Repository. And as part of that, we're going to cover what is the AWS Serverless Application Repository, and then what are nested applications and how do they solve these challenges with serverless architectures. And finally, we're going to talk about sharing serverless applications both internally across your teams or publicly with the world if you would like to. Then we'll close with some examples and demos. So what is a serverless application? Well, the first thing you need to do to learn about serverless applications is to meet SAM. SAM is our serverless application mascot. And SAM itself stands for the Serverless Application Model. AWS SAM is a CloudFormation extension and companion CLI tool optimized for building serverless applications. It defines serverless-specific resource types such as functions and APIs. It also now defines layers and applications, applications being the resource type of nested applications, which we'll discuss in detail today. It's important to note that while SAM defines its own resource types, it also supports anything AWS CloudFormation supports. So it's not limited in that way. It's an open specification with an open source implementation available in the AWS Labs GitHub repository. To use SAM, you define a SAM template in YAML, which specifies what resources should be created. In this example, we have a serverless function, a DynamoDB table, and an Amazon S3 bucket. Now, when you pass that template to AWS CloudFormation, CloudFormation will create a stack, which contains the actual resources specified by the template in your account. So here's an example SAM template. The top 2 lines tell AWS CloudFormation that this is a SAM template, and it could contain these special resource types specific to serverless. The next section, the resources section, is where you define what resources that AWS CloudFormation should create. Now, one important thing to note about SAM is that the AWS serverless function resource that you see is a special resource type provided by SAM, which simplifies the syntax needed for common serverless use cases. In this example, in addition to creating the Lambda function itself, it also creates an API gateway and takes care of all mappings and permissions needed. So what this means is what looks like one logical resource in this template actually expands to 7 AWS resources that get created. This is done to simplify this use case of an API invoking a serverless function. So now that we have a better handle on serverless applications in SAM, I'd like to talk about some unique aspects of serverless architectures. The first thing people tend to notice when building serverless applications is that serverless is a natural fit for event-driven architectures. This is because of the convenient native event sources offered by several AWS services. For example, Amazon SNS can trigger a Lambda function, or Amazon SQS can trigger a Lambda function. Amazon DynamoDB has Lambda integration through DynamoDB streams, where a Lambda function can be asynchronously invoked to process stream events. So since individual functions are now exposed at the infrastructure level, the architecture becomes much more granular, exposing more internal details of a system. So before serverless, managing infrastructure usually meant managing complexity around networking, multi-AZ redundancy, and EC2 autoscaling groups. With serverless, you're not worrying about autoscaling groups and availability zones and redundancy there, but now a single logical microservice will contain multiple Lambda functions. Some are synchronously invoked to service customer API requests, while others are invoked asynchronously to perform backend processing. So now that we understand serverless architectures, I want to dive deeper and talk about some of the challenges working with a system like this. The first challenge I'd like to talk about is infrastructure complexity specific to serverless architectures. So since serverless application details are now present at the infrastructure layer, infrastructure complexity grows with application complexity. This diagram makes the infrastructure look nice and neat, which works well for slides. However, the reality is it could look something like this, for example. This diagram shows a slightly more realistic view of the different relationships between the Lambda functions and various resources such as Amazon S3 buckets or Amazon DynamoDB tables. However, this only captures the synchronous side of this microservice. How about the async processing side? Again, this seems pretty neat and tidy, but what happens if we actually zoom into the details of this infrastructure? Okay, so there's quite a bit more complexity here. So this is an example of what that async processing side could look like, but where did all this complexity come from? Well, let's break it down piece by piece. Our synchronously invoked Lambda functions wrote to a DynamoDB table. We use that as the trigger point for our async processing. We have a Lambda function that triggers off of that DynamoDB table stream and publishes an event to an SNS topic. We connect SQS queues to the SNS topic in order to create two async processing pipelines. The first processing pipeline forwards the events to an Amazon Elasticsearch service domain via Amazon Kinesis Data Firehose for search and analytics. The second pipeline puts an object into an S3 bucket, which triggers a Lambda function to perform some sort of transformation, let's say a media conversion of some kind, and write the data back to the S3 bucket. For example, an example media conversion could be image thumbnail generation. However, in a production system, you have to plan for issues like message processing failures. So best practice is to attach a dead letter queue, or DL queue, to Lambda functions that do async processing. A DL queue is another SQS queue where messages that the Lambda function repeatedly fails to process can be stored for further troubleshooting. Here we've added one for each async processing Lambda function after the SNS topic. Now, with so many DL queues, you'll need a way to monitor them and get notified if they have messages. We can accomplish this by attaching CloudWatch alarms to the DL queues. Now, in a production scenario, if those alarms go off and notify you, what do? You'll need to troubleshoot what issue was causing the messages to repeatedly fail and fix it. Then, once the issue is resolved, you'll need to redrive the failed messages again. We can do this by attaching a Lambda function to the DL queues that will redrive DL queue messages back to the original SQS queue. The event trigger for the DL queue redrive Lambda can be initially disabled, then a DevOps person can have a procedure to enable it to redrive the failed messages, clearing the alarm, and then disable it again. So although an initial serverless prototype may be pretty simple to build, more complexity is required to make this truly production ready. This example is a good segue into the second architectural challenge I'd like to talk about today. Duplication of effort. When working with serverless applications, common patterns emerge and are duplicated across architectures. Let's look at some examples from the previous async processing pipelines. We went into detail about Lambda function DLQs, monitoring them, and redriving failed messages. The two things I want you to note about this is that, one, the pattern is duplicated multiple times just in this single architecture, and two, there's nothing business differentiating about it. However, it's required in a production system. As you start to look across multiple architectures, you'll start to see other patterns that are duplicated across them. For example, forwarding events to an Elasticsearch domain for search and analytics. This is a larger portion of our architecture, but again, while the data may be business specific, there's nothing business differentiating about the architecture and infrastructure here. Yet, engineers spend countless hours building and rebuilding these pipelines and learning and relearning the DevOps pain associated with if they do not follow best practices. This kind of duplication is pervasive throughout the tech industry and is not only limited to DevOps. It's also present in core application functionality. For example, document and media conversions are a very common thing that need to happen in an application, generating thumbnails, converting one document format to another. API authentication and authorization, for example, OAuth authentication. Payment processing, notifications, third-party integrations, these are all common and, generally speaking, not business differentiating functionality of an application. Now, after core application function logic, as I've shown, also DevOps, so feature toggles, being able to turn certain features on and off at runtime, CI/CD pipelines, event and DLQ redrive was the example we just went into a lot of detail about. Business intelligence as well, so asynchronous data processing as well as analytics. So as we've shown, there's also duplication on the non-customer facing side of an application. While all of these elements are critical to running a successful production application, they are not business specific. This means companies are still spending lots of engineering dollars on duplicative, undifferentiated heavy lifting. Now, of course, AWS is constantly working to build managed services to reduce this load on customers. However, due to finite resources, AWS must prioritize across its customers' needs. So another possibility is to give customers the power to build and share these common pieces of serverless infrastructure among themselves. This brings us to the main topic of this webinar, which is nested applications with the AWS Serverless Application Repository. This feature allows you to do exactly this. So let's talk about what is the AWS Serverless Application Repository, or AWS SAR, as we like to call it. AWS SAR is a managed repository for serverless applications that allows you to store and share reusable applications and easily assemble and deploy serverless architectures in powerful new ways. You don't need to clone, build, package, or publish source code to AWS before deploying it. Instead, you can use pre-built applications from SAR in your serverless architectures, helping you and your teams reduce duplicated work, ensure organizational best practices, and get to market faster. There are two ways to use SAR, as a publisher and as a consumer of applications. First, let's start with publishing. Publishers can publish their SAM template to SAR using the SAM CLI, AWS Console, or AWS SDK. Any Lambda function or layer code referenced in the SAM template is copied into SAR, so publishers and consumers are decoupled from one another. Publishers can upload new versions of the app and use semantic versioning to let consumers know if a change is a simple patch or a breaking change. Here's a screenshot of the AWS console for publishing an app to SAR. You enter certain metadata about the application, such as a name, author, and homepage URL, then specify a SAM template to upload as the first version. Alternatively, apps can be published via the SAM CLI. You simply specify your application metadata directly in your SAM template, and then use the SAM publish command to publish it to SAR. In this example, we have metadata defining the name of the application, a short description, an author, if it's open source, an open source SPDX license ID, and then it has pointers to the license text as well as the README. You can attach labels, reference to a homepage URL, and then define a version that should be uploaded that this current template should represent, as well as a source code URL pointing to the specific version of this app. You specify this in your SAM template, and the SAM publish command does the rest. Once published, you can view and edit your published application in the AWS console. The other side of SAR is the consumption side. So consumers of applications of SAR can easily discover and deploy apps via a public website for public applications or the AWS Lambda console for both public or privately shared applications. Since SAR hosts Lambda function or layer code and API definitions used by the app, deploying an app becomes as simple as a few clicks in the AWS Lambda console. The Lambda console's create flow allows you to search SAR for public or private applications to deploy to your account. Once you select an app to deploy, you can view additional information about it, such as its license, any special permissions needed by the Lambda functions created in the app, or even the full SAM template. You then specify a stack name and any required parameter values, click deploy, and the app is deployed by CloudFormation directly into your account. This is great for deploying one-time standalone apps into your account. However, there's an alternative way to deploy SAR apps, through adding them as nested applications in your SAM template. So now that we know what SAR is and some of the features it provides, let's talk about nested applications. Nested applications is a feature of AWS SAM that builds off a concept in AWS CloudFormation called nested stacks. AWS SAM defines a resource type called AWS Serverless Application. This resource can be included in your SAM template just like any other resource. However, the AWS Serverless Application resource is a reference to another SAM template containing its own resources, its own isolated app. In this case, the nested app template contains a serverless function and a DynamoDB table. However, it can include any resources that SAM supports, which is SAM's serverless resources, as well as any CloudFormation resources. When the top-level template is passed to AWS CloudFormation, CloudFormation uses it to create what's called the root stack. It then creates another nested stack containing the resources defined in the nested app template. Although the nested stack is a distinct stack in CloudFormation, you only need to deploy the root stack, and AWS CloudFormation automatically orchestrates updates to all nested stacks for that root stack. Similarly, in a CI/CD pipeline situation, you only need to deploy the root stack, and CloudFormation will handle deploying any nested stacks that are included in that template. One of the key features of nested apps is that they are natively integrated with AWS SAR. This means you can use this feature to nest an app from SAR in your SAM template just by referencing its ARN and semantic version. Let's take a look at what that looks like. In your SAM template, you define a resource of type AWS Serverless Application. You then reference its SAR application ID, which is an ARN value, along with the semantic version you'd like to deploy. Finally, you enter any required parameters for the application. While the syntax is very straightforward, it does require looking up the application ARN and its required parameters. So to help that, SAR provides a shortcut in the Lambda console. Once you've selected an app in the Lambda create flow, you'll notice a button near the top labeled Copy as SAM Resource. Clicking this button will automatically copy the nested app syntax for this application to your clipboard. Then, you simply paste the app straight into your SAM template. It's important to note that nested apps are not simply standalone apps deployed as part of your stack. You can also wire them to other resources defined in your template using CloudFormation's intrinsic functions to reference them. In this example, the nested app requires an AWS code build project name. If our template defines a code build project elsewhere in the template, we can pass it as a reference into the application parameter. Now, not only can values from your template be passed into the nested application as a parameter, the nested application can also produce outputs that you can wire to other resources in your application. For example, this nested application creates an S3 bucket and outputs the bucket name as the template output called build logs bucket name. We can reference this value using CloudFormation's getAt intrinsic function, which is short for getAttribute, like this. We pass getAt the logical ID of the nested application, the string outputs, and then the name of the template output whose value we would like to get. This makes it easy to compose nested applications as a logical part of your larger serverless architecture. Combining these two technologies, AWS SAR and nested applications, enables you to build sophisticated serverless architectures by reusing services that are authored and maintained independently, but are then easily composed via AWS SAM and the AWS Serverless Application Repository. Nested apps modularize your serverless architectures and are inherently reusable, reducing duplication and further simplifying infrastructure management. For example, in our async processing architecture from earlier, we can convert these repeated patterns into apps, like this. Here, we've encapsulated the DLQ plus alarming plus redrive functionality into apps, which we can then nest for each SQSQ or async lambda function in our template. We had also identified that storing events from an SNS topic to an Amazon Elasticsearch domain is another common use case across architectures. We can even convert all of that functionality into a SAR app and then pull it into our architecture as a nested app as well. Note, that app may also nest our DLQ app, and that's okay. You can have multiple levels of nesting. This is just a small example, but the possibilities for reducing duplication are endless. This strategy also helps reduce complexity by modularizing larger systems into discrete, manageable building blocks. Another benefit of this modularizing of your architecture is that the functionality for each individual app can be integration tested in isolation. Once you've integration tested that the app performs what it should be doing, this reduces the number of overall system level tests that need to be written to verify the larger system that it's integrated against. One of the most powerful aspects of nested applications is that they can be used not only to reduce duplication within your own project, but also across your teams or even the world. SAR's integration with AWS Identity and Access Management, or IAM, provides resource-level control of each application, enabling you to publicly share applications with everyone or privately share them with specific AWS accounts. It's actually a common misconception that SAR apps must be public. This is not true. In fact, by default, SAR apps are private to the publisher's account only. However, SAR does allow for private sharing between AWS accounts. This can be done easily through the AWS console or via the AWS SDK or CLI. Here's an example of an app that is shared with 4 different AWS account IDs. To add another account, click the Add button, enter the new account to share the app with, and click Save. Now the newly entered AWS account will also be able to search for and deploy the private application. SAR does also support publicly sharing apps with any AWS account. The AWS console has a toggle button for making an app public. Once an app is public, it can be searched for and deployed by any AWS account. So hopefully this gives you an idea of the power of nested applications, but let's take a look at some more examples just to continue seeing how we can reduce duplication throughout our serverless architecture. Here's a very simple example of wanting to maintain a real-time copy of a DynamoDB table. So you can have an app that creates a Lambda function that connects to the DynamoDB stream of one DynamoDB table and then replicates that data to another DynamoDB table. This can be used to maintain a local copy. Let's say, for example, the DynamoDB table on the left is the one used for OLTP or online user transactions. And then, however, we want to perform some scans or something for offline processing on that DynamoDB table, this app can maintain a copy table. And so you can scan that copy table without risking availability to your users. Another example is media conversions. Here we have an image resize app that triggers off of objects placed into one S3 bucket. It performs a resize operation and puts it into another S3 bucket. This could be used for thumbnail generation, for example. You can do other conversions on images like blur effects or other effects. However, there are other media conversions that can be done as well. You could have apps that change documents from one format to another, for example, Markdown to HTML. Another use case is integrations with third-party apps. So you can have an app that presents a Lambda function that allows you to send messages to a Slack channel, for example. Another use case is, for example, processing tweets. So you can use an app that connects with the Twitter API and then performs a search against Twitter and then invokes your Lambda function to perform whatever processing you'd like to do on the results of that Twitter search. I'd actually like to demo that use case for you so you can get an idea of just how easy and powerful these serverless applications can be when you nest them into your own application. Okay, so on my screen, I have the Lambda console. You can see that there are different ways to author a Lambda function, and one of the options is the AWS Serverless Application Repository. So I have that selected, and I'm presented with a search. So I can search for public applications or private applications. In this case, I'm going to look for that Twitter event source app, and it pops up right here. Now at this point, I could click and I could deploy it manually to my account. However, I actually want to nest this into a SAM template that defines the tweet processor itself. So as I said earlier, SAR provides this really simple experience where you can click this Copy as SAM Resource button. I'm going to switch over to a SAM template that I have ready here. So this is an AWS SAM template in YAML format. It has a tweet processor function that I wrote. This function is very simple. All it does is just log whatever event it received. So enter something into the log. However, now I need to insert the Twitter event source app. It's copied to my clipboard, so I can paste. And as you can see, an AWS Serverless Application resource type has been added to my account. If I want, I can rename this logical ID to something else. I'll just leave it. And it's already filled in the application ID and the latest semantic version of this app. Now you can see kind of a lot of text here. This app has many features to it, and so it has many optional parameters that if you wanted, you could override. I'm not going to do that. I'm actually going to just remove those optional parameters. Now, one required parameter you need is your actual Twitter search text. So for this demo, I'm going to use just hashtag serverless, and then this is specific to the Twitter API, but I'm going to filter out native retweets. Then we need to pass it our tweet processor function name. Again, this processor function is defined right here. So we need to enter its name. And if you look at the documentation for this app, it says, note, this must be a function name and not a function arn. So the CloudFormation ref intrinsic function will resolve to this function's name when this is deployed. So I can reference it simply just like this. If I wanted to test my search text before running it against this app, I can do that just using the Twitter search API. So I can put in my search and then look at the results, and I can see that these results seem to be in line with what I'm looking for. So by providing this serverless function that logs this message, and then simply pasting in this app, I should be able to deploy this using the SAM CLI. So I can now package this template. So what this is doing is this is just packaging up my Python code using the SAM build command. It's running some unit tests against it, and then running the SAM build command, which builds and packages the tweet processor function. Now the SAM package command is taking the Lambda code, the Lambda function code, and uploading it to an S3 bucket. And now we're ready to deploy. So we can use the SAM deploy command to deploy to this packaged file. It's actually local to my directory, so I can just pass this. We need to name the stack. So let's call it AWS Webinar. And then AWS CloudFormation requires certain capabilities in order to deploy. So Lambda functions require this capability IAM in order to create the IAM role associated with the Lambda function. And the new nested apps feature requires a new capability called capability auto expand, which indicates that nested SAM templates should be processed. So running this command will call CloudFormation and start deploying this template, which again contains that nested Twitter event source app. So if we go over to our CloudFormation console and refresh, we'll see we now have this AWS webinar stack being created. And if we check on the status of this, you'll see it's creating the IAM role right now. And that's completed. It's creating the Lambda function. And now what we see is it's creating a nested stack. So it's creating this Twitter event source app as an AWS CloudFormation stack. And if we click on that, we'll see that the Twitter event source app is being deployed into our account. So this is very powerful because now when I'm writing my function, what you'll notice is I'm writing an app that can interact with the Twitter with tweets. However, I did not have to write any code against the Twitter API itself. All I have to write is my Lambda function that receives a list of tweets in JSON format and then I can do something with them. So, for example, I could perform sentiment analysis on it, or I could put that data into some kind of analytics platform. If I'm curious about tweets on a certain subject, the possibilities are really endless. This app is taking away the complexity of working with the Twitter API. Okay, so this app is continuing to deploy. It's created a Lambda function. And again, even the internal details of this app, if you want, there's a README for the app that does explain the app architecture and how it works and what it does. But you can see that using the app was as simple as just pasting this into my SAM template. So the other thing I wanted to show you is that when I look at my CloudFormation stacks now, there's this AWS webinar stack. That was my root stack that was created, that's currently being created. And you can see that CloudFormation natively understands when one stack is nested. So this nested stack contains that Twitter event source app. So clicking on it, CloudFormation, right now it's still creating, but for example, if I tried to delete that stack, CloudFormation will actually warn me that performing operations directly on a nested stack may result in unstable state where things are out of sync, and it's not recommended. So again, although these are distinct stacks, CloudFormation does recognize that they are related, and it directs you to perform operations against the root stack only. At this point, both of these stacks have finished creating, and our tweet processor function has been created. So if I click on that, I'll be able to go to the Lambda function console. I can see the configuration of that app and click on the monitoring tab and see that my function has been invoked. So if I now go to CloudWatch logs, my expectation is to see a lot of tweet JSON in my logs. And that's exactly what I see. This is a lot of JSON. There's a lot of data with each tweet. But if I search for that hashtag serverless, you can see that the full text of the tweet is here, along with the metadata of the tweet as well. And my function is being passed arrays of many, many tweets, anything that's found from this search. So again, what this demo showed is that I was able to use a serverless app. I was able to embed it in my SAM template as a nested application, and I was able to immediately start writing logic to perform tweet processing without having to know anything about the Twitter API or its internals. Okay, so that concludes this webinar. Thank you so much for joining. Again, my name is James Hood. I have my Twitter handle there in case you'd like to reach out. And I encourage you to visit the AWS Serverless Application Repository, check out the apps we have there, and also build and contribute your own. Thank you very much.